and it is a pleasure to be here speaking with you tonight. I think we're going to do a series of 4 talks, and this will be the first one. We're going to kind of loosely follow the seasons through a series of really fascinating topics. And since it's wintertime, and also I think in celebration of Halloween, we're going to do one on bones and skeletons tonight. So I think that's a great topic. But just by way of introduction, my name is David Lukas, and I have spent my life working as a freelance naturalist, a lot of it in the Sierra Nevada. Some I don't know who's there, so I don't know who I've met. But I know a lot of people in the Sierra Nevada. One of my projects when I was here is I lived in Groveland for 12 years or so, being a hiking guide, naturalist guide in Yosemite. And one of my projects was writing a book called Sierra Nevada Birds. And I mention this because I still have a few copies left. If anyone's interested in getting a copy, just drop me a note. I can put my address in the chat, my email address, and you can send me a note. And this is a compact field guide companion, no pictures, just detailed life histories of the behavior and seasonality of birds in Sierra Nevada. A great resource if anyone's interested. And I have spent my life going out into the wild, going out looking at natural history, taking notes, coming back to my library here, which is 4 sides around me, and researching what I see, what kind of questions I come up with, and then putting what I learned together into talks, presentations. I've given thousands of presentations and walks that I've led, and writing books and writing magazine articles. My most recent project is up on the screen. Lucasguides.com is a weekly nature newsletter, and I encourage everyone to check it out and to subscribe. It comes as an email once a week, and every week I cover some fascinating topic about the natural world. One of the topics I just covered was about how autumn colors are used as signals for aphids because trees want to communicate with aphids. Great topic. And tomorrow's topic comes out on Thursday. Tomorrow's topic is going to be about birds, so you might be interested. But tonight we're going to talk about the bones and skeletons underneath birds. And, we all love looking at birds and let's see, we all love looking at birds and uh, studying their behavior and identifying them. But underneath all of this is a skeletal structure and some bones that's controlling and shaping everything that's going on with birds in their lives. So I want to just tonight go under the surface and kind of begin to understand some of the form and function of a bird. And before I get started, I just want to mention that in tonight's talk, the diagrams I'm using come out of 2 books that have been my lifelong companions, incredible resources. So if you're interested, and as you'll see, the diagrams are fantastic. Either one of these books or both of these books are a great resource and are a fun way to learn a lot about birds. Especially the Handbook of Bird Biology is very easy to read, clear and large print, great illustrations, great photographs, just a fantastic book. And then in conjunction with images from these books, I'm just grabbed some photos from the internet to help illustrate our educational talk tonight. So let me start with this. There are about 10,000 species of birds in the world. And one of the things that's really remarkable about all of these 10,000 species is that when you look at this robin, this is basically the same size and shape of the vast majority of birds in the world. So yes, of course, there's some exceptions, larger and smaller and different shapes. But by and large, the vast majority of the world's 10,000 birds basically all have this exact shape, and they're all, say, smaller than a football, at least. So small and this shape. So my question to you is, why is this? Well, birds need to fly, and they are shaped by the demands of flight. So all aspects of their bodies, their skeletons, their bones, their muscles, everything is geared around the demands of flight. And in order to fly, birds have had to drastically reduce their weight and create this streamlined shape. And over millions of years of evolution, they have found the perfect aerodynamic shape. And once you've reached this shape, you can't easily tweak it. You can't add or change things to this. You can't shift the ratio of weight or the proportions of different things because you're going to mess up the aerodynamics of flight. And in fact, when birds converged on this form and this basic size, they haven't changed in about 15 million years because you cannot tweak this without messing up flight. So keep that in mind because everything we're going to look at tonight is all designed for flight. And I mentioned that the birds of the world are all basically the same size and shape because that's not true for other groups of animals. So I've thrown up a few mammals, for example. I picked a whale, a giraffe, and a little shrew. And look at the size differences and the shape differences. You can't even begin to compare the many, many different sizes and shapes that mammals have. And if we talk about flight and the demands of flight, well, fish are basically flying as well, but they're flying through water. But even fish have an incredible range of sizes and shapes. Here I have like a manta ray, a guppy, and an eel or a lamprey, incredibly different sizes and shapes in fish. So again, birds are unique in all basically having the same size and shape. Okay, so there's a problem with that though. So imagine if all the birds in the world, let's just say for argument that they're all exactly like this. How do they tell each other apart? In terms of evolution, animals need to be able to separate each other and have competition so they can figure out who's dominant and who's using different resources. They need to recognize each other. They have to have different niches. So if all birds basically look like this, how do birds separate themselves into different species? Well, there's three ways that birds have that do not add weight and do not mix up this aerodynamic equation. So one way is color. Birds obviously have different color patterns. That doesn't add any weight. It doesn't mess up aerodynamics. The other one is they have different songs and different vocalizations. That's how they can tell each other apart. And then the third way is their beaks. So the beaks on a bird weigh almost nothing. And because a beak weighs almost nothing, it frees them up to modify it in countless ways. And let's see, maybe I should have my pen here. Every one of these bill shapes and styles allows for a different lifestyle, allows for different diets, allows for different environments. It allows birds to separate out and use different niches in the world because their bills are so different without adding weight. So for example, this is the lower beak on a pelican, and it weighs about like a paperclip. Even though it's this big, it's probably a foot long, it weighs virtually nothing. And that's true for bills of all sizes. So that is a way that birds use to separate each other. Um, so bills are something that we're going to see on the surface, but I want to go under the surface of all these feathers and look at what's going on tonight. And tonight we're going to talk about the heads, the bodies, the wings, and the legs, all of the basic um, skeletal structures. And keep in mind that every part of what we're going to be looking at is features that are devoted to flight. And this includes making radical changes in your skeletal structure. You want to reduce the weight. You cannot fly if you weigh a lot. So one way to reduce weight is to fuse bones and eliminate bones. And this is something we're going to see throughout all parts of a bird tonight. So since we've already mentioned beaks, let's start with their skull, their heads. And there's a lot going on here. So what's the first thing you notice when you look at a bird skull like this? So here is, I think you can see this here too. This is one, this is a cormorant, I believe, cormorant skull. The first thing you notice is this gigantic space right here. Look at this gigantic hole in their head. And what is this? This is their eyeball. Birds have huge eyes. They are visual creatures, and the eyes are so big that the brain is basically an afterthought, and it's tucked up on end and shoved into the back of the skull to make room for these massive eyes. So does this mean that birds are dumb because they have little tiny brains pushed into a back corner? Well, no, because the eyes are actually doing a lot of the cognitive neurological functioning that the brain would do. So imagine this. A bird is flying along at high speed through a bunch of branches. There's a branch coming straight at it. The eyes see the branch. They send the signal and the image to the brain. What do we do about this? The brain thinks about it, says, let's go left. It sends the signal back to the eyes. Look left, go that way. Bam, you've hit the branch. You don't have time to send signals back and forth to your brain to make decisions when you're flying at high speed, especially through complex space and complex objects. So the eyes have to be doing that processing without sending messages back and forth to the brain. So the eyes are actually really important for that. And the eyes are so big that they smush together in the center of the skull. And remember, you want to reduce weight. So you don't need this bone in between your eyeballs. Get rid of some of that bone. And the eyeballs smush together and push against each other in the center of the skull. These are all places where they've reduced and eliminated bone between the eyeballs. So, for instance, a red-tailed hawk, which is about 3 feet tall, has the same size eyeball as a human being, despite being much smaller. Their eyes are huge, okay? So is this what we see when we look at a bird? Do we see these big, gigantic eyeballs? Well, no, we don't. We see these little tiny beady things sticking out. So what's going on here? Well, birds have a unique bone called a sclerotic ring. And this is a circular collar of bone that sits on top of the eyeball and holds it in place. So here's a side view of it. And basically the skin connects to this ring of bone and pushes down on the eyeball, and a little tiny bit of it bulges up through the center of this ring. So when we see this, there is a ring of bone here, and we see a little tiny thing in the center bulging out as the beady little eye of a bird. And what's unique about this sclerotic ring is that only one other group of animals in the world has ever had these, and that was dinosaurs. And this is a key piece of evidence that scientists use to show that birds evolved and are closely related to dinosaurs because they share this very unique bone. But that's not the only thing that's unique about bird eyes. Look at how they're positioned on the skull as well. So they're on the side, a little bit forward of center. And the advantage of that is they're looking out into the world on each side, and they can see predators coming. Each eye is looking out like this. And if you look at the field of view that they can see, each eyeball on each side is basically seeing this much space on each side. Well, that's great for looking for predators coming at you. You can see a wide range of view on both sides, almost, but not quite behind you even. The disadvantage is when you have eye vision separated like that, is that you're only seeing two-dimensionally on each side. You need your vision to overlap to see three-dimensional space. And so here's the human view. We see with one eye for a little bit on each side, but the vast majority of our vision is three-dimensional in front of us because we're reaching out, we're manipulating complex objects in complex space, so we need three-dimensional depth, okay? So birds have vision out to the side. The eyes are positioned on the sides of the skull so they can see predators, but they can't see two-dimensionally, but they can see three-dimensionally in one area in front of them. So again, this is the range of what each eye is seeing on each side, and those ranges overlap in front of the bird, and look where they overlap. They start exactly right here at the tip of the bill. That's exactly the point where the three-dimensional vision starts, right where the tip of the bill is reaching out into the world, picking up tiny insects, tiny seeds. That's where they see three-dimensional space from that point out. And when you look at this rock dove, that's exactly what the eyes are doing. Look, they're focusing down exactly on the tip of the bill, right where it's reaching out and picking up food that it's eating and manipulating. Okay. So what else do you immediately notice when you look at the bird skull? Where are the teeth? So the bird has a jaw. So when you have a jaw, you would expect there to be teeth because you need to grind up and chew food. But what's the problem with teeth? Well, there's a lot of problems with teeth. One is they weigh a lot. Teeth are basically heavy, dense bones. They weigh a lot. So what supports heavy teeth? Well, you need heavy bones to support the heavy teeth. And if you have heavy bones, what moves them? Well, you need heavy muscles to move and operate those heavy bones that are holding the heavy teeth. So when we look at just a schematic of a bird, everything about this bird is about flight and operating around the center of gravity, okay? So if we imagine this bird has the heavy teeth here, heavy bones, heavy muscles, what's going to happen? Well, the head is going to become very heavy and it's going to fall face first into the ground around this pivot point in the center of its body. Well, how do you counteract that? Well, you'd have to add a ton of weight to the tail so there's a balance front to back. Well, all of a sudden, you've added a lot of unnecessary weight just by having heavy teeth. So what birds have done is they've taken the chewing function of teeth and moved that to the center of the body. They have moved this chewing function right here to the exact center of gravity to a very heavy muscular stomach called a gizzard. So at like Thanksgiving or Christmas, when you have a turkey or a chicken, you find the gizzard in the center, this really thick, heavy muscle stomach, which uses muscles to squeeze and crunch food. A bird will eat little bits of rock, put it inside of this muscular stomach. Then when they eat food, they just slurp it down in their bill, swallow it whole. It goes into the gizzard, and then the muscles do the chewing, and it's happening all right here at the center of gravity. They've taken the weight of the teeth and moved it there. And not only does it balance front to back, but here is this head-on view, and the same thing. The center of gravity is right there, side to side. Here's the wings coming out, the keel that holds the flight muscles, and right in the center is the balance, the heavy pivot point, front to back, side to side. But this absence of teeth is not the only thing that's remarkable about their jaws. So if we look at this upper jaw, which is called the maxilla, it is an outgrowth of the bone of the skull. It's continuous with the bone of the skull. And the lower jaw, the dentary, is separate, a separate bone, and it articulates with the skull. So because of that, I always assumed that when a bird opened its beak, it just lowers its lower bill since the upper bill is part of the skull. And when we looked at the picture like the skull we were looking at, that looks exactly like what's going on, right? It looks like the lower jaw is just dropping like this. Well, that's not what's going on. Birds actually have an elegant mechanism in their, I guess, jaws or the beaks. And what's going on is that there is a muscle that would pull down on the dentary. This articulates at a point right in here, which means it goes up and down around that pivot point. The muscle pulls it down, and the dentary goes down like this. So the dentary bone is going to go down like this. And as the tip goes down, the base pivots up like this. And as the base pivots up, it rotates another bone called the quadrat bone. And that pivots here at the base. And as the lower jaw goes up like this and pushes on the quadrat bone, it gets pivoted up like this. And as the quadrat bone gets pivoted up, it pushes out at the base here and pushes another bone called a jugal bone. And as that bone gets pushed out, it pushes the lower mandible up. So at the same time that the lower mandible goes down with one muscle, it is operating this system of cogs, which raise the upper bill the same distance at the same time. So even though this upper bill, the maxilla, is continuous with the bone of the skull, the bone right here at the base is very thin and flexible like a cartilage. It's called the nasofrontal hinge, and it allows the upper bill to go up. And if you find, like my skull that I showed you here is dried and old, but if you have a fresh skull, you can actually push on the upper mandible and it'll go up and down because of this flexible hinge right here at the base. Right here at the base is the flexible hinge that lets the upper mandible go up and down as the lower ones opened and closed. So it's a really elegant way of allowing a bird to open its upper and lower bill at the same time, the same distance, with only one muscle and a very simple, elegant system of cogs that are moving the different bones. It's really cool. So when we add feathers to a skull, we get a very complex of small feathers. In fact, 80% of the feathers on a bird are on its head. They use all these feathers for social signaling. They can raise and lower different feathers, and um, uh, so they're really important to birds. So when we look at this, we know right away that this bird actually has this huge eye here. It's got this sclerotic ring right here, and then that little eyeballs bulging out through it. One other thing we can see with the head view like this before we move on is let's look at the eyelids. So a bird can open and close its eyelids, right? Goes to sleep at night. When a bird goes to sleep at night, it closes its eyelids. When it wants to rest, to shut out the world, it closes its eyelids. Well, that's great, but what if you're flying through the air? So you're flying along, this is great, then a piece of dust goes in your eyeball. And you're like, oh, shoot. And you're like, you can't take your wing and rub your eye to get the dust out. You don't have fingers to kind of move it around. You're stuck, right? And you can't be blinking your eyes to try to move the piece of dust around. So when birds are flying, they have another eyelid called the nictitating membrane. I don't know if you can see that small print. Nictitating membrane, which is a translucent eyelid that doesn't go up and down like this. It goes front to back like windshield wipers, and it cleans and moistens the eyeball as a bird flies, and they can see through it because it's translucent. So it's a really elegant way to keep the eyes wet and clean by constantly doing these windshield wipers as they fly without having to open close their eyelids. So let's continue. Let's consider the wings on a bird and what's going on here. So if we look at the bones of a bird wing, I want to compare them to a human arm. And what's amazing right away is look at how similar they are. They have basically all the same bones and the same proportions. So we have like the shoulder here, the elbow here, the wrist here, and the hand here, right? And same bones and basically all the same proportions throughout. Okay, but there are some big differences. Okay, one big difference is look at the wrists on humans. We have so many bones in our wrists, and what do we do with that? We can do all of this incredible movement and flexibility. We can maneuver and pick up really complex objects. We can use fine tools, everything. So we need a lot of bones for that flexibility. Well, imagine if you're a bird and you're trying to fly and you've got all of these bones here and you're flying along. Whoa, this is really hard. I can't control this. The only way I could control this is with muscles, right? Oh my gosh, I have lots of bones, lots of muscles. Not going to work. So birds have they've eliminated all of those wrist bones and reduced it to two very simple bones here at the base of the fingers that has a very limited movement, like this, just very efficient, very limited. You don't need to do all this crazy stuff, just a simple, efficient motion over and over again with each wing beat. Okay, so they've gotten rid of all those bones. Well, how about our fingers? Look at how many bones we have in our fingers to let us do all of this incredible dexterous manipulating of objects in our world. Birds don't need that. So let's get rid of all those bones, okay? So they've reduced it down to one finger, which is the index finger. Here, basically one finger is half of the wing on a bird is a single finger. They have the middle finger here. The middle finger is a tiny little bone here. And then there's a little vestige of the thumb here, another little tiny bone here. But basically, their wing is one finger on their forearm. And when we add feathers to all of this, you can see all of that here. So again, let's see, shoulder, elbow, wrist, and hand here. And the skin on a bird basically goes like this. So we don't see the shoulder and the elbow. We see the forearm and the hand. And if you go from the wrist here, this is the wrist on a bird. If you go down from this point, let's see if I can do this right here. That line at the wrist divides it into the hand. These feathers are the hand. That's half of the wing, and the other half of the wing is the forearm. Okay. And these feathers here on the hand are the propeller. So the tips of these three or four fingers out here, or these feathers out here, are the propeller that moves the bird forward. If you clip off a tiny bit of the tips of those, maybe a quarter inch, a bird can't fly because you take away its propeller. But you can remove 40% of these feathers on the forearm and a bird can still fly. So these propeller feathers are absolutely critical for a bird. There's a few other things we can see here. On this one is from the shoulder here to the wrist here, there's a tendon going across right here that connects them. So from their wrist to their shoulder, there's a stretchy tendon here. So as a bird's flying, that stretchy tendon gives them the ability to move in the air. They're not rigid, just doing this. They're actually kind of bouncing and flexing as they fly with this stretchy tendon between the forearm and the wrist. And then on the trailing edge of the wing, they have another tendon. So this one's called the patagium up here. And then on the trailing edge, they have another tendon, which is a thick fibrous tendon called the postpatagium that goes along the trailing edge of these bones. And it holds the base of all the feathers. The base of every single wing feather goes into that thick fibrous tendon and holds it rigidly in a flat plane. It doesn't let the feathers do crazy up and down, stuff like this. You need to create a uniform, dependable, flat surface in order to have flight. And that tendon holds on the all trailing edge of the wing that holds all the feathers in that flat plane. Not only does the tendon hold the feathers in that flat plane, but this bone here on the forearm, the ulna bone, between the elbow and the wrist, the forearm, the ulna bone, has holes in it, and the base of each of those secondary feathers goes into a hole along this bone. So here again is a pelican forearm. This is the ulna on a pelican, and look at the holes running up and down the whole length of it. Each one of those holes is where the base of a feather fits and it gets locked in place, and then the tendon holds them all in a flat plane. Super elegant way of creating the flying surface on a bird. Um, I mentioned this little vestige of a thumb here, and this is a little complex, but I'll mention why that's important. So when a bird's flying, the steeper it turns its wings up in a vertical way, the steeper it turns its wings up in a V up vertically, the more resistance to the air it has and the slower it goes. And they use that when they land. So if they're flying along straight through the air and then they come in for a landing, they turn their wings up to cup the air and slow down and drop down onto a branch. Well, the more you cup your wings up, you begin to create turbulence as air goes over the top of your wing and swirls behind the wing like this. And turbulence destroys lift. And if you have turbulence, the bird would just crash straight to the ground because there's no more lift. So that thumb with a couple of little fingers, a couple of little feathers on it, three little feathers on it, they will lift that just barely above the surface of the wing and it'll streamline the air so it goes over the top of the wing and to the back without creating turbulence. So it allows the bird to turn its wings up, slow down, and drop gracefully onto a branch while just doing little tiny micro maneuvers with their thumb to control their descent as they land on a branch. A nice use of that vestigial bone. So when we look at a wing, kind of put it all together, we have the shoulder in here, we have the elbow, which we don't see, they're tucked up inside the body. The wrist is here, and then this is all hand, this is all forearm. This is what we see on a bird when they're flying. And since we've been talking about feathers, let me just do a little quick aside about feathers. All of the feathers that we see on a bird are called contour feathers. They streamline the bird. They get rid of all the sharp edges. They smooth everything out so the air can flow over it like over a teardrop. All of the contour feathers on the bird that we see externally have two unique characteristics. One is they have a central shaft going up the center here. And then coming out from that central shaft are two veins made up of barbs. So these barbs are little filaments coming off here. And all of this material is keratin, which is the same material as in your fingernail. That's what makes a bird wing, bird feather. So there's about 9,000 barbs coming out as filaments off of the central shaft. And then all of those 9,000 barbs are held together with little Velcro hooks called barbules. And there's about 1 million barbules on a contour feather holding the barbs together. And that creates this streamlined and waterproof surface. So basically, a bird is wearing a Gore-Tex jacket. It's flying around the world. It's perfectly dry. This is great. Okay. Underneath the Gore-Tex jacket, they have a different kind of feather called a down feather, which differs in not having that central shaft. And it doesn't have the barbules. So all of these barbs just kind of do this frilly, frothy mass, which traps air and keeps the bird warm, just the same as in our down coats and our down sleeping bags. So basically, a bird is wearing a warm down coat, and over that is wearing a Gore-Tex jacket. Bird is flying around the world. Oh, this is great. I am dry and I am warm. Everything is perfect. Uh-oh, there's something wrong. What is it? Well, those are too many coats. The bird can't feel anything. It is perfectly warm, perfectly dry. It can't tell what's going on in the world around it. Excuse me. So they have a third kind of feather called a phyloplume, which is basically just central shaft and a little bit of barbs at the tip. You really don't see them at all. So basically just shafts sticking out all over its body through its other feathers. And these are antennae that tell it what's going on in the world around it. It can sense air currents. It can sense changes in pressure. It can sense where the feathers are laying in relation to each other as the bird moves and helps the bird adjust in the air. If you remove these phyloplumes, a bird can't fly because it can't sense the world around it. So another important feather. And one final thing I'll mention about feathers before we move on. Feathers weigh a lot. They're actually pretty heavy and they keep you warm, but they keep you almost too warm. And you don't need all those feathers. So birds are actually mostly naked. So here's a loggerhead shrike, and here's a schematic diagram showing these white areas are naked areas, and the stippled areas are groups of feathers. And basically, a bird does a comb over all its nakedness, right? So there's a reason for this. Not only do the feathers weigh a lot and keep you too warm, you don't need all that weight. You don't need all that warmth all the time. But feathers are also controlled by muscles and are controlled by nerves. And if you have all of these nerves and muscles going out to every part of your skin, that adds a lot of weight as well. And you're just too warm. So concentrate your feathers into little groups, excuse me, and concentrate and eliminate some of those nerves and muscles and just have the bare minimum of what you need. So let's move back to the bones and to the legs on a bird. So here we have the leg of a bird next to the leg of a human. And again, a lot of similarities, but more differences in this case with the legs. As a lot of you know, bird legs are pretty amazing. And when we look at a bird, basically the skin on the bird is like this. We don't see the knee or the hip. We just see the calf and the ankle and the foot and the toes is all we're seeing below a bird. So when we look at the comparison between the two, a lot of the same bones, but different proportionality and a lot more differences than with the wings. So let's start with the ankle and the foot bones. So we have a lot of ankle and foot bones. I want you to just stretch your foot out in front of you and just rotate your foot around and just feel how you can move around. That's possible because of all of those bones in our feet. Birds don't need all of those. So they've reduced them to a single bone called a tarsometatarsus, which is just a long bone. It's the foot is reduced to one bone, which is a long bone, and it acts like a lever. And this is what throws the bird up in the flight and lets them run. So imagine if our foot was 2 times longer, maybe 3 times longer than it is now. Imagine how fast we could run or how high we could jump. That's exactly what a bird is doing. They got rid of all these little tiny bones and all that flexibility and made one giant lever to throw them into the air in flight. And then all of our toe bones here are very simplified in birds. They have the toes, 3 toes forward, 1 toe back is the common pattern. Um, and then, so basically a bird is standing on its toes and then its foot is up to its ankle, which is here halfway up is what we're seeing on a bird. Another difference is the lower leg. We have a fibula and a tibia, which gives us that rotation. When you rotated your foot, you are rotating it around the fibula and the tibia. Birds don't need that. They don't need to rotate their feet. A bird just needs a very simplified leg movement. So imagine a duck in water. Its legs are just going back and forth over and over again. Whoosh, whoosh, whoosh. Very, very simple, very, very efficient. They're not doing a lot of crazy maneuvering. So imagine a rabbit being chased by a predator. What does a rabbit do? It's going to be bouncing and zigzagging wildly as it tries to get away from a predator. Well, a bird doesn't need to do that. If a predator comes after a bird on the ground, it just uses these long tarso-metatarsus as a lever, throws itself in the air, its wings come out, and it's gone. It doesn't need to do this weird running and stuff like that. So get rid of that flexibility and simplify it into one bone, the tibiotarsus, which they use as a shock absorber for when they land. That bone absorbs the impact when they land. So all of these foot bones here are reduced to one tiny bone on a bird. I don't know if you can even see it. There's a tiny little dot right there. That's the last true foot bone on a bird. Then we have the halix, which is basically the big toe rotated around to the back. And essentially, a bird has an opposable toe, the big toe, the same way that we have an opposable thumb on our hands. And birds use that for perching. So the bird has generally 3 toes forward, 1 toe back, and they grip onto branches that way. And for perching birds, these toes are all at the same level. They all come out of the foot at the same level. If it was a ground bird, this halix, the hind toe, would get in the way, so they move it up here to get out of the way. But generally, for most birds in the world, the 4 toes are on the same level, 3 toes forward, 1 toe back. And look what else is going on here. From the knee coming down, the muscle coming down the back of the leg goes over the ankle, turns into a tendon. The tendon goes down, goes through the foot, and attaches to the tip of each toe. And then when a bird sits on a branch, 3 toes forward, 1 toe back, and bends its leg, the tendon stretches and pulls the toes tight. So when a bird lands on a branch at night, 3 toes forward, 1 toe back, and then sits down, that bending of the back leg pulls the tendon, the toes close, and it just clenches on a branch, and you can just sit there and fall asleep at night without having to try to hold on with its muscles all night long. And another way that birds use this is imagine an owl. So you have an owl up on a branch, right? Let's see. So you have an owl up on a branch, and it's looking down. There's a little mouse running along on the ground. The owl leaps into the air, and you've seen photographs like this, right? Where the owl's flying down, its talons are out, the poor little mouse is running along. It grabs the mouse and then collapses into the ground. And guess what happens with its talons? They crush with a killing blow because the tendon gets pulled. So they grab it and collapse into it and let gravity deliver the killing blow without having to squeeze it with muscles and try to kill it that way. They just use this mechanism to crush and kill right away. It's super elegant. Let's see. I think we're doing okay on time. We've got a couple more slides here. So let's kind of pull it all together here and look at the skeleton as a whole. There's a lot going on here and a lot of fusion. Okay. So the first and most important piece of fusion that's happening in a bird skeleton is in the spine. So from this point to this point, all of the vertebrae, and in this case also the pelvis, the pelvic bone, are all fused into one rigid backbone. Okay. So think how we use our backs. So we can do all of this crazy stuff with our backs. And how can we do that? Well, we do that because we have really big, strong core muscles, back muscles that allow us to maneuver like this, but is that going to work for a bird? So imagine a bird's flying along like this, and its back is doing all this as it's flying. It's like, wow, this is super hard, right? That's not going to work. So birds have a very rigid backbone. Let's see if I can do this. Really rigid backbone, very limited wing movement. Remember that? Very efficient platform for delivering muscle power to wings for efficient flight. All possible because that very rigid backbone. Okay, well, that's great. What's the problem with that? Well, you're very rigid in the world. And how do you don't have hands, you don't have arms to reach out and pick up food. So they put all the flexibility that they've lost with their back into their necks. So every mammal in the world has 7 neck vertebrae. Birds have anywhere from 11 to 25 neck vertebrae, which give them incredible flexibility in their neck. They can move their heads around, they can reach out, they can pick things up, they can turn around, they can preen the feathers on their back or preen their tail. They can look, their eyes don't move. Their eyes are so big, they're kind of locked in place. So they compensate for that by moving their head a lot. And all of that happens because they have an incredibly flexible neck. And then they have a little bit of flexibility here, a couple of free vertebrae that are not fused in their tail. So they can wiggle their tail, they can use it as a rudder in flight, they can fan it out for courtship or social displays, right? So they have some flexibility in their tail, a very rigid back, and an incredible flexible neck. So that's the basic pattern on a bird. And then there's 2 times in a bird's life where they need to support their weight. So when a bird is standing on the ground, it's supporting its weight on its legs. So they have a broad platform here, which is 14 vertebrae and their hip bone or pelvis fused into one big platform for muscle attachment. Their tail muscles, their leg muscles, and their abdominal muscles attached to this platform to support their weight while they're standing. The other time a bird is supporting its weight when it's flying. It's got its wings out, it's hovering in the air, it is hanging all of its weight on its wings. So they have a broad platform here called the keel or the sternum, and this is where they support all their weight when they're flying, right? And this keel or sternum is so important to birds that if humans were able to fly, we would need a 6-foot keel to support the muscles we would need to fly. Okay. Another really cool thing here you're going to see on the skeleton is the ribs. Okay, so what are the ribs doing? The ribs are creating a basket to protect all of a bird's vital organs. And when a bird is flying, they're under incredible amounts of stress. They're fighting the wind, they might be fighting each other, they're doing these wild, crazy maneuvers, tremendous mechanical forces on their body. And that rib cage has to protect all of their vital organs through all of that activity. Well, the birds have big, thick, stout ribs. No, their ribs are actually very fragile. They're little thin ribbons. They're almost nothing. So how do those thin little ribs protect the internal organs without adding weight to the body? Well, they have an incredible solution, this little thing called the uncinate process, which is just basically, you can see it's a little thumb sticking out, a little flange sticking out from each rib. It's a little thing sticking out off of each rib. It's a little bony protuberance that goes over the neighboring rib, and basically all the ribs hug each other. And together they create a very strong, like kind of a wicker basket that holds all of the internal organs, protects them by cooperating and working together without adding extra weight. It's a phenomenal solution. One other thing that the ribs have, which is really cool, is right in the midpoint is a little, I guess a little hinge, you could call it here, little flexible point right here. And when a bird is flying, it is burning an incredible amount of energy. It's basically a metabolic furnace going at full speed. It's burning an incredible amount of energy. It needs an incredible amount of oxygen to keep the fire going. But in fact, birds have very small lungs. Their lungs are about 2% of their body volume, and in humans, it's 20%. So their lungs are much, much smaller than ours, but their demands are much, much higher. So the way they compensate for that is that the ribs are hinged like this, and in flight, with each wing beat, the rib cage partially collapses and operates like a bellows that keeps the fire going. So the ribs are pumping oxygen through the bird's system with every wing beat as they fly because they hinge at this point, just like a bellows. Really incredible. Okay, so one last point we'll make. The center of a bird is really this thing called the pectoral pectoral girdle, which is three bones that come together. You have the clavicle, which is the wishbone or the furcula here. You have the humerus, which is the first major bone of the wing, and then you have the scapula, which is the shoulder. And those three bones come together. The wings are actually separate from the body. And so you need a pillar to connect the wings to the body, and that is this caracoid, which is a stout bone that connects the wings to the body. And with each wing beat, you're pulling down with great force. You don't want to crush your body. So this caracoid keeps the body from being crushed. And then these three other bones work together to shift the power and the weight of wings and wing muscles in the body and make it all work together. And there's a very elegant solution. So you have the three bones here, they call it the furcula, the humerus, which is the first bone of the wing, and then the scapula, the shoulder bone, and then the caracoid is what joins it to the body. Well, you have the keel here, and on the keel of a bird are massive breast muscles. 30% of a bird's weight are breast muscles, the pectoral muscles. These power the wings. So these massive muscles here connect from the keel to this first bone of the wing, the humerus, and pull down with great force with every wing beat. Woo, woo, these massive breast muscles are pulling down like this. Well, that's great. This is really powerful for flight. A bird can fly really powerfully and really fast. But the problem is, how do you lift your wings? Bird doesn't have muscles up here. That would be extra weight, and it ruins the center of gravity. So what they do is they have another muscle called the supracaracoideus muscle here underneath the big pectoral muscles. And it's a thin sheet of muscle that goes up underneath. It goes up along the caracoid and through a little hole where the three bones come together. There's a little hole called a triceal canal. It comes up through that, connects to the top, and then lifts the wings. Here's another view of it here. Here's a massive pectoral muscle pulling the wings down. And here it is on the straight on view. This huge muscle from the keel up to the humerus is pulling wings down. So the muscles pull down, the wings come down. And then underneath it is a thin sheet of muscle that goes up through the hole over the top, connects to the top, and lifts the wings. So one muscle pulls down, pulls the wings down. This thin sheet pulls down, and because it goes up and over the top, it lifts the wing when it pulls down. And all of your weight is right here, down low on a bird. You're not ruining your aerodynamics or anything. And these two muscles works in parallel like this with each other, pulling the wing down, pulling the wing up, pulling the wing down, pulling the wing up, just like that because of this pulley system. You can actually cut this caracoid muscle, supracaracoideus muscle, and a bird can still fly, but it can't take off. So why is that? Well, when a bird takes off, it needs muscles to lift its wings up, push down, lift its wings up, and push down. But once a bird's flying, it's just basically doing this. And it's using a different force when it's doing this because, let's see, let's go back to this. This furcula, the wishbone, is a very flexible, elastic bone. So at Thanksgiving or Christmas, when you have a bird, a chicken or a turkey, everyone wants the wishbone and you try to break it, but it's too bendy, so you have to dry it out. Well, what's happening with that is that on every wing beat, when the wings come down, the furcula, this is the paper clip, but showing you the principle. Let's see. When the wings come down, sorry, it squeezes it, and then when you relax, it pops open, and that lifts the wings. You squeeze it with the big pectoral muscles, and then you lift it, and the elastic power of it pops the wings up. So that's why once a bird's flying, It doesn't need a muscle. It's just using the power of this flexing and flexing and flexing to power the upbeat without wasting muscle energy. But that doesn't work when a bird is on the ground. It needs to lift its wings up and poof, fly like that. Whew, I hope that makes sense. That's kind of complicated. Sorry about all that. So let's put it all together here. We have the little wiggly tail fanning out. We have the keel bone here with the big muscles attached to it, the shoulder, the elbow, and then the wrist dividing the wing. Here's the hand and the forearm. Conveniently, they're both different colors in this bird. You have this gigantic eye right here. All of this is happening under the surface in a bird in flight. And in conclusion, I just want to just marvel at the fact that birds have come up with all of these amazing way of reducing and streamlining their body and their bones, simplifying, fusing, eliminating to create the lightweight, very efficient flying machine that we love and appreciate today. So with that, that's the conclusion, and we can go to questions.